In problem number 5, we have two trains, one 350 feet long and the other 450 feet long, and they pass each other completely in 8 seconds when they are moving in opposite directions. If they were moving in the same direction, they'd pass each other completely in 16 seconds. And we're asked to find the speed of the slower train. Alright, well, let's first of all draw a picture here. I'm going to use arrows to represent the two trains. So I'm going to draw one arrow, kind of a shorter arrow. I'm going to call it train A, okay? And that's going to be the 350-foot train, okay? And I'm going to draw another arrow going in the opposite direction, a little bit longer. Label that train B, okay? So this represents the case where the trains are moving in opposite directions. And let's figure out how far the trains have to move in order to pass each other completely. All right. So we want to find the speed of the slower train, and in order to find that, we just need the distance and the time. Right? And we're given times. We're given 8 seconds and 16 seconds. And distance equals rate times time. So if we want the rate, it's just distance divided by time, and that's equal to the rate. Okay. So if we can figure out the distance that these trains have to move with respect to each other, and we're given the time, then we can find their rates. But the thing is that they're both moving, and we don't really know which train is faster, if it's the shorter train or the longer train, and if it doesn't really even matter which one's moving faster. So I'm going to define also a couple of variables. I'm going to call x the speed of the faster train, and I'm going to call y the speed of the slower train. Okay. Now let's think about what's going on here. We could consider this as an extreme case where, let's say for example that train A is standing still. Okay, we'll say its speed is 0. It could be 0. We don't know that yet. Probably not, because then it would take the faster train the same amount of time to pass it, whether no matter what speed it's or what direction it's going. But let's just look at the case where if A was stationary and then B is traveling along here, it first starts to pass the train at this point, and then it travels along. So here's B again, but it still hasn't completely passed train A until the back end of this train passes the back end of this train. So it won't completely pass the train until it's out here. Okay, so let's assume that's the same length. So how far does the train have to move? And let's just use the front of the train as our reference point. Okay, so the front of the train has to move from the front of train A until it's 450 feet beyond the back of train B. So this is 350 feet, and then it has to move another 450 feet in order to completely pass train A, if train A is standing still. Okay, so we have a total of 800 feet that train B would have to move to pass train A completely. And when they're moving in opposite directions, we know that happens in 8 seconds. So the speed of train B would have to be, so it's 800 feet in 8 seconds, so it would have to be moving at 100 feet per second. Okay. So that was the case if train A is standing still. So, but let's say that um, let's say that train A is moving and train B is moving, and they're moving in opposite directions. But let's say we're actually riding on train A. When we're riding on train A, as train B moves, we could, if we ignore the world around us and we're just focused on train B, we can almost think of ourselves as standing still, and train B is moving at, it looks like it's moving faster than it really is relative to the Earth. But relative to train A, it's actually moving faster because it's moving toward us and the speeds are additive. So what we can say is that the speed of the faster train plus the speed of the slower train has to be 100 feet per second. Okay? Does that make sense? Because the speeds are additive. If you're riding in a car and you're watching the oncoming traffic, if you were to imagine yourself as actually standing still, the oncoming traffic is going to look like it's coming at you faster when you're riding in a car going toward it than if you were sitting in the middle of the road and that same oncoming traffic was coming toward you and you're standing still with respect to the Earth. Okay? So, when the trains are moving in opposite directions, the speeds are additive, and to pass each other completely, I guess we can take the front of the train as our reference point. The front of the train would have to move 100 or 800 feet. Okay? So, alright, so let's look at the other case where the trains are moving in the same direction. And you guys have probably experienced this when you're riding in a car and a car beside you passes you. So you might be going at 55 miles an hour and that car might be going at 60 miles an hour. So it really doesn't, if you imagine yourself as being standing still, that car that's passing you doesn't look like it's going all that fast, right? It looks like it's going pretty slow. It doesn't just zip past you at 50 or 60 miles an hour because you're going 55 miles an hour. So it actually looks like it's going like 5 miles an hour. All right, so here's train A, and then we also have train B. I could draw it like this, train B, and they're just starting to pass each other here. I should probably draw train B a little longer so that it's the 450-foot train. So, in order, let's again imagine that train A is standing still, and and train B is passing train A. Then, in order to pass train A, train B would have to travel. Ooh, no, that's not a very nice looking line. Let me try that again. Okay, so your train B, if it's 450 feet, it would have to move a total of 800 feet again. But we're told that when they're traveling in the same direction, it takes 16 seconds for the trains to pass each other, right? And like I said before, their relative speeds, if you're riding on train A and train B is passing you and they're moving in the same direction, then relative to your vehicle, your train, train B is going to look like it's going slower than it would if you were actually sitting on the side of the tracks and watching them pass each other. Okay, the speed relative to the Earth is faster than the speed relative to train A. Okay, so when the trains are traveling in the same direction, their speeds are. We need to look at the difference of the speeds because that's going to tell you how fast this train is traveling with respect to train A. That's sort of their relative speeds. So let's see. I guess we got to go back here because so train B would have to travel 800 feet to pass train A completely, and it would have to do so in 16 seconds. So if we take 800, and divide it by 16, we actually get, what is that? So that's like, so 100 over 2. So that's 50 feet per second. All right. So when the trains are traveling in opposite directions, the difference in the speeds is 50 feet per second. All right. So we have two equations and we have two unknowns. Okay, here's our two equations. Now this looks like a fairly easy set of equations to solve because, let me scroll down and give myself a bit more room. We have x plus y equals 100, and we have x minus y equals 50. And we can just add those up, and the y's will go away, right? Because y minus y is 0, so we end up at 2x is equal to 150. So x is equal to 75. All right? And then that means because the sum of the speeds is 100, then the slower train would have to be 25 feet per second. All right? And that's what we're asked to find, the speed of the slower train. So there you go, the slower train. Now we still don't know which train is moving slower. We don't know if it's train A or train B, the 350-foot train or the 450-foot train. But the slower train, whichever one is moving slower, is going 25 feet per second. All right. So there's your answer.